Alright, so now that we understand what the determinant is and how to calculate it, I'm going to teach you about how to invert a matrix. So let's say we have a matrix A, and that matrix A is going to be multiplied by some vector x, and that vector x is going to contain the solutions to a system of equations that we have, and then we have another vector v, or vector b, sorry, and that contains the solution. So what does this look like? Let's say we have a system of equations like this: 2x plus 3y equals to minus 1, and then 3x minus y equals to 2. So the way we would write this is, we would make our matrix A, which contains all the coefficients of this side, so that's going to be 2, 3, 3, minus 1, and then our vector of solutions is going to be x, y, and that's going to be equal to minus 1 over 2. So we already discussed in the last video that in order to find the values of x and y using matrix methods, what we need to do is we need to invert this matrix A and multiply it by the vector b such that we get a solution for x and y. So inverting the matrix and then multiplying it by the vector b, so inversion, which is denoted by minus 1, and then minus 1, 2. Now, in order to get to this step, we need to define what the inverse of a matrix is. And basically, having a matrix of any dimensions A, the inverse of that matrix is defined as follows. We're going to get the determinant of that matrix, so that A is going to be the determinant first. And then, because that's a number, we are allowed to divide that by a single number. And we're going to divide, what are we going to divide? The transpose of the cofactor matrix of A. So cofactor matrix we're going to denote as C, and then the transpose of that is denoted as to the power of t. So remember, transpose is essentially we just exchange rows by columns, and that's all it is. So because this is just a number, this is just like dividing by some fraction, like 1 over 2 times the whole matrix. So basically we'll multiply every element of that matrix by 1 over 2. So that's just to give you an example, but this is by definition what the inverse of a matrix is. And you might sometimes see this written as adjoint of matrix. Adjoint of matrix, but this tends to have different meanings in different fields. And for example, in quantum mechanics and physics, the adjoint of a matrix may have a different meaning to that. So basically what we will do is we just call it the cofactor matrix of that matrix A. And so how do we go about finding the cofactor matrix? Well, first of all, we need to define what the cofactor matrix is. So the cofactor matrix is the minor of a matrix. So minor is another type of matrix, but it is actually going to have its signs change. So basically, it is going to be all the elements of that minor matrix, but it is going to follow the following pattern. So we're going to multiply each of these elements, or each of the corresponding elements, by these signs. So if we have a 3 by 3 matrix, for example, this is what we're going to have. So we're going to multiply each element. So let's say this is M11, M12, M13, and so on and so forth. So that's what it is. But how do we find the minor matrix first? Well, that's a really good question. Let's have an example. Let's have A equals to 302, 2, 0, minus 2, and then 0, 1, 1. First thing we need to do is, well, we're going to find the minor of this matrix. So minor, denoted by M, is going to be a larger matrix. Actually, not larger, it's going to be a 3 by 3. It's going to be the same size. But the way we're going to define it is each element will be the determinant of one of these elements. So for the first element, for example, we're going to take this. And what we're going to do is we're going to essentially get the determinant of the elements that are exactly diagonally across. So the same process that we did for finding the determinant of a 3 by 3 matrix, we're going to block this column and this row But instead of multiplying this determinant by 3, we're just going to calculate the determinant. So this is going to be 0, minus 2, 1, 1. And this is going to become the first element of that minor matrix A. Now for the second element in the first row, we're going to take this one, and basically we're going to block this column and that row, and we're gonna calculate the determinant of the remaining columns, which is going to be 2, minus 2, 0, and 1. So this is what's going to be the second element in that first row. And then finally for the third row, for the third column in the first row, we're going to have this element, and then we're going to block this column, block this row, and then we're going to get the determinant of the remaining columns, which is going to be 2, 0, 0, 1. Alright, so that's basically what we're going to have. And now obviously we need to construct the second and the third row, and we're going to have the same procedure. We're going to start with the second row, and now what we're going to do is we're going to block this row and this column, and we're going to have the determinant of the remaining two rows, which is going to be 0, 2, 1, 1. And hopefully you can see where this is going. Now for the middle one, we're going to block this column and this row, and then we're going to have the determinant of the remaining elements, which is going to be 3, 2, 0, 1. And I'm just going to keep going like this. Hopefully this works really well as an exercise for you to understand what this process is really doing. So 0, 2, 0, minus 2. We start filling. So if you have the third row, for example, you're going to block this column, block this row, and then use the determinant of the remaining elements. And then we'll repeat the procedure. So it's a lot of repetition here, but hopefully you get an idea of how this works. So this is going to be our minor matrix, and then obviously we need to calculate those determinants. So we're going to have the following result. So our minor matrix is going to be the following. We're going to have 2, 2, 2, minus 2, 3, 3, and then 0, minus 10, 0. So this is our minor matrix. Now for the cofactor matrix, what we're going to do is we're going to get each of those elements, but we're going to apply that little sequence that I showed you. So we're going to multiply each of the elements by the corresponding signs. So we're going to have plus, minus, plus. So basically this is going to lead to the following cofactor matrix, which is going to be, this is going to be 2, minus 2, 2, it's going to be 2, 3, minus 3, and the last row is going to be 0, 10, and 0 again. So that's going to be our cofactor matrix. And now that we have this, what we will need to do in order to calculate the inverse, we're going to have to transpose this matrix. So I'm just going to do that here at the top. So let's go back. I'm going to get rid of this whole thing. So the transpose of our cofactor matrix is going to be essentially, we're going to exchange each row by a column. So this row is going to become the first column. So that's going to be 2, minus 2, and then 2. And then the second row is going to become the second column, 2, 3, minus 3. And then the last one is going to be this. And hopefully that gives you some sort of idea of what's happening here. So that's the transpose of the cofactor matrix. So that's the first thing we needed. The second thing is going to be calculate the determinant of this matrix. So that of A, I'm just going to do it directly here. So we're going to start with the first element, 3 times 0, minus 2, 1, 1, minus 0. So we're not even going to bother with that one. And then the last one is going to be plus 2, 2, 0, 0, 1, which is actually, no, it's not 0, sorry. So this is going to be 3 times 0 times 1 minus 2, so that's going to be plus 2. Plus 2 times 2 times 1, so that's 4. And this is equal to 10. Finally, we can find the inverse of this matrix, which is going to be cofactor transpose over determinant of A. So this is going to be this whole matrix, but we're going to divide it by 10, so 1 over 10. And what's this going to be? Well, if we remember that when we have a matrix times a constant, we're just going to multiply that constant by every element in that matrix. So our final answer for the inverse of A is going to be the following. We're going to have every single element divided by 10. So the inverse is going to be 0.2, 0.2, 0, minus 0.2, 0.3, 0, that's going to be 1, and then 0.2, minus 0.3, 0. So this is going to be our inverse. That's our final answer. Now, how do we check this? Let's see what we can do with Octave. So let's open Octave again, and let's try and find the inverse of this matrix. So I'm just going to draw it here. Now remember, essentially there should be a function that allows us to calculate the inverse directly, and there is in fact. So I'm going to write the matrix here. A is equal to the following, so that's 3, 0, 2, second row is 2, 0, minus 2, and then the last row is going to be 0, 1, 1. That's our matrix A. And now the inverse of that is going to be denoted by this function, so that's inv of A. So this is going to be equal to this. And is that the same that we got here? Well, let's check. Let's have a look. And we have 0.2, 0.20. Well, yeah, the minus is implied, but essentially you get the idea. Minus 0.2, 0.3, 1, and then 0.2 minus 0.30. So yes, the answer is correct. Now you might be wondering, is there a function for calculating minors and cofactors of a matrix? I'm not very sure about minors. I don't think those are built into Octave. But essentially, the only reason you would need to calculate minors and cofactors of a matrix is just to find the inverse. Just to find the inverse. And because these operations are already built into the function inverse, we don't actually need to go through the whole process, because what we would want to do in order to solve a system of equations is to find the inverse, and there's already built-in function for that. So in the next video, what we're going to do is we're going to apply this sort of procedure to actually solving a system of linear equations. So that's what we will focus on in the next video. And then the videos after that, we're going to focus on systems of equations and how to solve them. Because remember, it is very easy to find a unique solution when you have a square matrix. But what happens when you don't have a square matrix? What happens when you have a system that is like this? 2x plus 3y minus z. And then equals 0. 2x minus y plus 5z equals to, let's have minus 3. Now obviously you don't have a square matrix there because you have more unknowns than you have equations. So is there any solution to this? No. But there are other things that you can do to sort of get an idea of what a solution might look like. And that's what we will do in videos, some videos later on. But for now, we'll just focus on square matrices and systems of equations where you have the same number of unknowns and the same number of equations.